In nonlinear systems, we're now solving systems that could be a circle in a line, a parabola in a line, two parabolas, a circle and a parabola, and so forth. We're no longer looking at where two equations of lines intersect. So we may get 1, 2, 3, and even maybe more values, more points as answers. So first thing I want to do is show you this first type. If you have a nonlinear system where one of the equations is, in fact, a linear equation, the substitution method is probably to your advantage. So start by solving for y. 4x minus 5 here would be what y would be equal to. So that little block there is what I am going to substitute everywhere in the second equation that I run across the y. We get 4x squared minus 8x plus, and instead of y, we're putting that little block in. So we get 4x squared minus 4x. The 5's cancel, equals 0. Now that actually does factor, so I can solve it that way. The 4x factors out and leaves behind an x minus 1. And if I set each one of those equal to 0, I'm going to end up with an x value of 0 and an x value of 1. What this tells me is that since I've ended up with two x values, I'm looking for two corresponding y values. The nice thing about you having used the substitution technique is that I can now use this little block to help me generate my y values. The first one, y equals, now I'm going to use an x of 0 the first time. 4 times 0 minus 5. So my y value is negative 5 when x is 0. Now we'll plug in an x value of 1. Y is equal to 4 times y value of 1 minus 5. 4 minus 5, so our y value is negative 1. There's our first nonlinear system, and it has generated exactly 2 points where that parabola and that line intersect. Let's look at this second example. The nice thing about it is you really don't even have to know what it is that the nonlinear systems are, whether they're parabolas or circles. You can do it either way, when you know or if you don't know. Now, I want to illustrate the elimination process, even though this one, too, would be perfect with substitution. But we're going to use the elimination process just to show you how nice it can be. In order for them to eliminate a variable here, it looks like it's going to have to be the y's. So I'm going to multiply my whole second equation through by a negative 1. The first one didn't change, so I'm just going to rewrite him. The second one, I multiply all the way through by a negative 1. This gives me negative y equals negative 1 plus x squared. Now I'm ready to add them together so that the y's are eliminated and I can solve for some x's. The y's cancel when I add the two equations together, and I end up with 0 equals x to the 4th minus x squared, and my y's cancel. That actually does factor and solve very nicely like the last example. So I'm going to factor out the x squared. It leaves behind an x squared minus 1. That actually factors further into x squared times x plus 1, x minus 1. So I actually generate 3 x values here, an x of 0, negative 1, and positive 1. I get those by setting each one of these factors equal to 0 and solving for x. Since I have found 3 x values, it means that I'm going to be looking for 3 corresponding y values. We can go right back up to one of the original equations to solve for our corresponding y's. I like the second one. It's just a little shorter and smaller, so I'm going to use that. Y is equal to 1 minus x squared. And the first x I'm going to plug in is 0. 1 minus 0, that was nice. Now I'll plug in a negative 1. That's 1 minus 1 is equal to 0. Oh, that's a nice one also. Let me ask you a question. Is this going to change at all if I plug a positive 1 in there? No, it's actually going to generate a 0 for y as well. This particular system, nonlinear system, has generated exactly 3 solutions.